Welcome to this video on quantum physics, a century of mystery, discovery, and innovation. We will journey through 100 years of revolutionary science that transformed our understanding of reality itself. This show is brought to you by the Series of Thoughts team as part of their Science Foundations program. We begin with Chapter 1, the birth of quantum physics. The dawn of new physics occurred between 1900 and 1925. In 1900, Max Planck introduced the quantum hypothesis, suggesting energy comes in discrete packets called quanta. Let's look at the pioneers of this revolution. Max Planck, the reluctant revolutionary, introduced energy quanta. Albert Einstein, the quantum skeptic, proved light's particle nature. Werner Heisenberg developed matrix mechanics and the uncertainty principle. Next is wave-particle duality, the quantum paradox. Louis de Broglie proposed matter waves in 1924. Erwin Schrödinger developed the wave equation in 1926. Quantum objects behave as both waves and particles, challenging classical physics. Heisenberg's revolutionary insight in 1927 gave us the uncertainty principle, showing fundamental limits on knowing certain pairs of properties simultaneously, such as position and momentum. This shattered the deterministic worldview of classical physics. Chapter 2 focuses on the quantum revolution and its architects. Niels Bohr and the Copenhagen interpretation introduced the complementarity principle. Wave or particle descriptions are mutually exclusive but necessary. This view states that observation causes the wave function to collapse, giving the observer a fundamental role. The quantum atom shows Bohr's model, where electrons occupy discrete energy levels. Quantum mechanics refines this, describing electron wave nature forming standing wave patterns in orbitals defined by quantum numbers. Albert Einstein's skepticism led to the EPR paradox in 1935, challenging quantum mechanics' completeness. He objected to, quote, spooky action at a distance implied by entanglement, believing in hidden variables to restore locality and determinism. John Bell's theorem in 1964 provided testable inequalities for local hidden variable theories. Alain Aspect's experiments in the 1980s violated these inequalities, decisively confirming quantum entanglement and nature's non-local behavior. Chapter 3 covers quantum mechanics today, interpretations and debates. Physicists are divided on what quantum mechanics truly means. These include the orthodox Copenhagen interpretation, disagreements, the many particularly on whether the wave function represents objective physical reality, and the subjective cubism, or merely a tool for these competing visions of quantum reality. All reproduce the same experimental predictions, but offer fundamentally different pictures of what exists and how reality operates at the quantum level. New frontiers explore quantum mechanics and consciousness. Research is investigating if quantum effects like coherence or entanglement play roles in neural processes, though the field remains highly controversial and skeptical. Chapter 4 explores quantum mechanics in the real world. Quantum technologies are transforming society. Quantum computing uses superposition and entanglement for massive parallelism. Quantum cryptography exploits quantum rules for theoretically unbreakable encryption. Quantum physics powers everyday technologies. Examples include solar cells, LEDs, MRI machines, GPS accuracy relying on atomic clocks, and semiconductors in electronics. Lasers and quantum dots are also quantum applications. Inside a quantum computer, qubits exist in superpositions of 0 and 1. They use entanglement operations to explore solution spaces exponentially faster than classical computers for specific problems, despite major engineering challenges. The year 2025 has been declared the International Year of Quantum Science and Technology by the UN, celebrating 100 years since matrix mechanics and recognizing quantum physics' transformative impact on science and society. Chapter 5 discusses outstanding mysteries and the future. The greatest mystery is the quest for a unified theory, reconciling quantum mechanics with general relativity. Quantum mechanics describes the small scale, while general relativity describes gravity and the cosmic scale, but they are currently incompatible. Some of the biggest unanswered questions include: what is matter fundamentally made of? Why does time flow only forward? Where did all the antimatter go? What are dark matter and dark energy? And how does quantum reality give rise to classical reality? Quantum gravity is the theoretical intersection where space-time meets the quantum. At the Planck scale, space-time is expected to behave as quantum foam. Testing this requires immense energy, prompting reliance on cosmological observations and indirect evidence. The promise of quantum computing and simulation is revolutionary. Potential applications include drug discovery, materials science, artificial intelligence, climate modeling, and fundamental physics simulation. Quantum technologies raise significant ethical and societal implications. These include threats to current security and privacy, potential economic disruption, the need for responsible innovation, and the challenge of promoting public understanding. Chapter 6 highlights key scientists who shaped quantum physics. Max Planck, the reluctant father of quantum theory, introduced the quantum hypothesis in 1900. By proposing that energy comes in discrete packets, E equals h times nu, he resolved the ultraviolet catastrophe, laying the foundation for modern physics. Albert Einstein provided crucial evidence for light quanta in 1905 with the photoelectric effect, and his work predicted stimulated emission. Yet, as a quantum skeptic, his 1935 EPR paradox highlighted entanglement and drove critical experimental tests. Niels Bohr, the architect of the Copenhagen interpretation, developed the Bohr model and the complementarity principle. He defended the orthodox view of wave function collapse in decades-long debates with Einstein, profoundly influencing quantum philosophy. Werner Heisenberg developed the abstract matrix mechanics and the famous uncertainty principle. Erwin Schrödinger formulated the more intuitive wave mechanics, including his wave equation, and highlighted the measurement problem with Schrödinger's cat. John Bell's theorem provided a testable framework to distinguish local realism from quantum mechanics. Alain Aspect's experiments confirmed the non-local nature of quantum entanglement, leading to the 2022 Nobel Prize. Richard Feynman was a pioneer in quantum field theory, inventing Feynman diagrams and the path integral formulation. He co-developed quantum electrodynamics and, in 1981, first envisioned the potential of quantum computing. Quantum physics, an unfinished revolution, stands on a century of profound discovery. Despite its successes, enduring mysteries remain regarding interpretation and quantum gravity. The journey continues as we move toward mastering quantum engineering.